The Sun is the star at the heart of our solar system. Its gravity holds the solar system together, keeping everything from the biggest planets to the smallest bits of debris in its orbit. The connection and interactions between the Sun and Earth drive the seasons, ocean currents, weather, climate, radiation belts, and auroras. Though it is special to us, there are billions of stars like our Sun scattered across the Milky Way galaxy. The Sun is the star at the center of the solar system, around which Earth and other planets revolve. It is the solar system's dominant and most massive body, with a radius 109 times that of Earth. The Sun's mass is 330,000 times that of Earth and accounts for more than 99% of the solar system's total mass. The Sun is composed of hot gases containing elements like hydrogen, helium, calcium, sodium, magnesium, and iron. The process of energy generation results from the enormous pressure and density at the center of the Sun, which makes it possible for nuclei to overcome electrostatic repulsion. The Sun has been shining for 4.6 billion years. The Sun is located near the edge of the Milky Way galaxy, approximately 25,000 light-years from the galaxy's center. Within our solar system, the Sun's immense mass, which accounts for over 99% of the solar system's total mass, creates a gravitational dominance that keeps all the planets, including Earth, in orbit around it. The Earth orbits the Sun in an elliptical path. The Sun is a star primarily composed of hot gases, including hydrogen and helium, along with smaller amounts of elements like calcium, sodium, magnesium, and iron. The Sun's core is hot enough to sustain nuclear fusion, where hydrogen atoms convert into helium, releasing vast amounts of energy. This process involves the fusion of hydrogen nuclei into helium, with about 0.7% of the mass converting into energy, according to Einstein's formula, E = mc². The Sun is at least 90% hydrogen by the number of atoms. The energy produced in the core travels outward, initially as gamma rays and kinetic energy. As the energy reaches the Sun's surface, known as the photosphere, it appears as visible light with a temperature of about 5,800 K. The Sun produces energy through nuclear fusion, primarily by converting hydrogen atoms into helium. This process, known as the proton-proton chain reaction, occurs in the Sun's core where extreme pressure and density enable nuclei to overcome electrostatic repulsion. In this process, 4 hydrogen nuclei fuse to form one helium nucleus, releasing energy as gamma rays and kinetic energy. About 0.7% of the original mass is converted into energy, following Einstein's formula, E = mc². This conversion of mass to energy allows the Sun to radiate energy for billions of years. The energy generated in the core gradually makes its way to the surface through radiation and convection, eventually being emitted as light and heat. The Sun is essential for life on Earth, providing light, heat, and energy that drives our atmosphere, climate, and various biological processes. The Sun's energy, produced through nuclear fusion, radiates into space, with Earth intercepting a small fraction. This solar energy powers atmospheric winds, oceanic currents, and nearly all biospheric activity, sustaining life through photosynthesis in plants, algae, and bacteria. The tilt of Earth's axis causes seasons by changing how directly sunlight hits each hemisphere, influencing temperature and climate. Additionally, the Sun emits ultraviolet radiation, which can be both harmful, causing sunburn and increasing skin cancer risk, and beneficial, stimulating vitamin D production. The Sun has several notable features related to its magnetic activity. Sunspots are regions of strong magnetic fields on the Sun's surface that appear as dark spots because they are cooler than the surrounding photosphere. Solar flares are sudden bursts of energy that occur near sunspot groups, releasing high-energy particles, X-rays, and radio bursts. Flares occur in the corona, and the energy released heats the surface, creating a superhot cloud that emits X-rays. These phenomena follow an 11-year cycle, with the number and size of sunspots and flares fluctuating. The Sun has fascinated humanity since the earliest moments of awareness, standing as both a life-giver and an enduring mystery in the sky. It rises each day with quiet certainty, marking the passage of time and shaping the rhythms of life on Earth. Ancient civilizations revered it as a deity, a symbol of power, or a guiding force behind the natural order. Even today, with all the advancements in science and technology, the sun continues to inspire awe, not only for its brilliance but also for its immense complexity. It is far more than a bright disk overhead, it is a dynamic, ever-changing star whose influence reaches far beyond what the eye can see. At its core, the sun is a massive sphere of hot plasma, composed primarily of hydrogen and helium. It sits at the center of our solar system, holding everything in place through its powerful gravitational pull. Without it, planets would drift aimlessly through space, and life as we know it would not exist. The energy it produces travels across vast distances, taking about 8 minutes to reach Earth, where it warms the planet and fuels essential processes like photosynthesis. This steady flow of energy sustains ecosystems, drives weather patterns, and enables the delicate balance that allows life to flourish. Despite appearing calm and constant from a distance, the sun is incredibly active and turbulent. Its surface, known as the photosphere, is in a constant state of motion, with vast currents of hot gas rising and falling in a process called convection. These movements create patterns that resemble boiling liquid, giving the sun a textured and ever-shifting appearance when observed through specialized instruments. Above this layer lies the chromosphere and the corona, regions that reveal even more dramatic activity, including solar flares and massive eruptions of charged particles. The sun's energy comes from nuclear fusion, a process occurring deep within its core where temperatures reach millions of degrees. Under such extreme conditions, hydrogen atoms collide and fuse together to form helium, releasing enormous amounts of energy in the process. This energy slowly makes its way outward, eventually radiating into space as light and heat. It is this fusion process that allows the sun to shine steadily for billions of years, providing a stable source of energy that life on Earth depends on. Human understanding of the sun has evolved significantly over time. Early observers could only speculate about its nature, relying on myths and philosophical ideas to explain its behavior. With the development of scientific methods and advanced tools like telescopes and space probes, we have been able to study the sun in remarkable detail. Scientists now monitor its activity closely, tracking sunspots, solar storms, and cycles that can have direct effects on Earth, such as disrupting communication systems and power grids. The sun also plays a crucial role in shaping the broader environment of the solar system. Its solar wind, a stream of charged particles flowing outward, interacts with planetary atmospheres and magnetic fields. On Earth, this interaction creates beautiful auroras near the poles, while also serving as a reminder of the sun's far-reaching influence. Beyond Earth, the solar wind helps define the boundaries of the heliosphere, a vast region of space dominated by the sun's presence. In many ways, the sun represents both stability and change. It has burned steadily for about 4.6 billion years and is expected to continue doing so for billions more, yet it is never truly still. Its cycles of activity, typically lasting about 11 years, bring periods of increased sunspots and solar storms followed by quieter phases. These cycles are a natural part of the sun's behavior, reflecting the complex interactions within its magnetic field. Understanding the sun is not just an academic pursuit, it has practical importance for modern society. As our reliance on technology grows, so does our vulnerability to solar activity. Powerful solar storms can interfere with satellites, navigation systems, and electrical infrastructure. By studying the sun, scientists aim to predict these events more accurately, helping to protect critical systems and reduce potential disruptions. The sun's significance extends beyond science and practicality into culture and philosophy. It has been a symbol of life, energy, and renewal across countless traditions and belief systems. Its daily journey across the sky has inspired art, literature, and spiritual reflection, serving as a reminder of the interconnectedness of all things. Even in a modern context, the sun continues to evoke a sense of wonder and curiosity, encouraging us to look beyond our immediate surroundings and consider the vast universe we are a part of. As we deepen our understanding of the sun, we also gain insight into other stars scattered throughout the cosmos. By studying our own star up close, scientists can develop models and theories that apply to distant stellar systems. This makes the sun not only vital to life on Earth but also a key to unlocking the mysteries of the universe. It serves as a natural laboratory, offering clues about the processes that govern the birth, evolution, and eventual death of stars. In this way, the sun stands as both a familiar presence and a gateway to the unknown. It is something we experience every day, yet it holds secrets that challenge even the most advanced scientific minds. Its light connects us to the broader universe, reminding us that our planet is part of a much larger cosmic story. Through continued observation and exploration, humanity continues to uncover new layers of understanding, revealing the sun not just as a source of light, but as a profound and dynamic force at the heart of existence. While the sun appears unchanging to the naked eye, its internal structure reveals a layered and highly complex system that governs how it produces and distributes energy. At the very center lies the core, where nuclear fusion takes place under immense pressure and temperature. Surrounding the core is the radiative zone, a region where energy slowly travels outward in the form of photons. This journey is not quick or direct. It can take thousands to millions of years for energy generated in the core to pass through this dense layer. Beyond that lies the convective zone, where energy is transported more rapidly by the movement of hot plasma rising and cooler plasma sinking, creating a continuous cycle that feeds the sun's surface activity. The surface of the sun, or photosphere, is the layer we see when we look at sunlight. It emits the visible light that reaches Earth and sustains life. However, this surface is far from smooth or uniform. It is marked by features such as sunspots, which are darker, cooler regions caused by intense magnetic activity. These sunspots can vary in size and number, often appearing in clusters and changing over time. Their presence is closely tied to the sun's magnetic field, which is constantly shifting and reshaping itself in complex ways. Above the photosphere lies the chromosphere, a thin layer that glows faintly and becomes visible during solar eclipses as a reddish rim. Beyond that is the corona, the sun's outer atmosphere, which extends millions of kilometers into space. The corona is surprisingly much hotter than the layers beneath it, a phenomenon that has puzzled scientists for decades. Despite its high temperature, the corona is very diffuse, and its faint light is usually overwhelmed by the brightness of the photosphere, making it visible only under special conditions. One of the most dramatic aspects of the sun's behavior is its magnetic activity. The sun's magnetic field is generated by the movement of electrically charged plasma within its interior. This field is not stable, it twists, stretches, and occasionally snaps, releasing vast amounts of energy in the form of solar flares and coronal mass ejections. Solar flares are sudden bursts of radiation, while coronal mass ejections involve the expulsion of massive clouds of charged particles into space. When these particles interact with Earth's magnetic field, they can produce geomagnetic storms that affect satellites, communication systems, and even power grids. The sun operates on a cycle of magnetic activity that lasts approximately 11 years. During periods of high activity, known as solar maximum, sunspots become more numerous, and solar flares and eruptions occur more frequently. During solar minimum, the sun appears calmer, with fewer sunspots and reduced activity. This cycle is an essential part of the sun's natural rhythm and provides valuable insights into its underlying processes. Scientists closely monitor these changes to better understand how the sun's behavior evolves over time. The influence of the sun extends far beyond light and heat. Its gravitational force holds the solar system together, ensuring that planets, asteroids, and comets remain in stable orbits. Without this central force, the orderly structure of the solar system would collapse. The sun also plays a key role in shaping planetary environments. For example, the intensity of solar radiation affects atmospheric composition, climate patterns, and even the potential for life on different worlds. In recent decades, technological advancements have allowed humanity to study the Sun more closely than ever before. Space-based observatories and solar probes have provided detailed data about its structure, composition, and behavior. These missions have revealed intricate details about solar winds, magnetic fields, and the mechanisms behind solar eruptions. By gathering this information, scientists can develop more accurate models of the Sun and improve predictions of solar activity. The study of the Sun is also crucial for understanding space weather, a term used to describe the conditions in space influenced by solar activity. Space weather can have significant effects on modern technology, particularly systems that rely on satellites and electronic communication. By improving our ability to forecast solar storms, researchers aim to minimize disruptions and protect vital infrastructure. This growing field highlights the practical importance of studying the Sun, especially in an increasingly interconnected and technology-dependent world. Looking ahead, the Sun will continue to evolve over billions of years. It is currently in a stable phase known as the main sequence, where it steadily fuses hydrogen into helium. Eventually, it will exhaust its hydrogen fuel and undergo dramatic changes, expanding into a red giant and altering the structure of the solar system. While this transformation lies far in the future, it serves as a reminder that even the most constant and reliable forces in nature are subject to change over time. The Sun remains a central figure in both scientific inquiry and human imagination. Its immense power, intricate behavior, and essential role in sustaining life make it one of the most important objects of study in astronomy. As research continues, new discoveries will deepen our understanding of this remarkable star, revealing more about its inner workings and its connection to the broader universe. Through this ongoing exploration, the Sun continues to illuminate not only our world but also our quest for knowledge. Beyond its physical structure and cycles of activity, the Sun plays a profound role in shaping life, time, and perception on Earth in ways that are both obvious and subtle. Every living organism is, in some form, connected to the energy the Sun provides. Plants convert sunlight into chemical energy through photosynthesis, forming the base of nearly all food chains. From the smallest microorganisms to the largest animals, life depends either directly or indirectly on this process. Even fossil fuels, which power much of modern industry, are remnants of ancient life that once relied on sunlight, making them a stored form of solar energy from millions of years ago. The Sun also governs the rhythms of life through cycles of day and night. This regular alternation influences biological clocks, known as circadian rhythms, which regulate sleep, metabolism, and behavior in many species, including humans. The rising and setting of the Sun has historically structured daily routines, agricultural practices, and cultural traditions. Long before mechanical clocks existed, people measured time by observing the Sun's position in the sky, using tools like sundials to track its movement. Seasonal changes are another result of Earth's relationship with the Sun. As the planet orbits and tilts on its axis, different regions receive varying amounts of sunlight throughout the year. This creates patterns of climate and weather that define ecosystems and influence how societies develop. Regions closer to the equator experience relatively consistent sunlight, while those farther away undergo dramatic shifts between long summer days and short winter ones. These variations affect agriculture, migration patterns, and even human psychology, demonstrating how deeply the Sun's influence is woven into the fabric of life. The Sun's light also shapes how we see and understand the world. Vision itself depends on sunlight or its reflections, allowing humans to perceive color, depth, and motion. The quality of sunlight changes throughout the day, from the soft hues of dawn to the intense brightness of midday and the warm tones of sunset. These shifts have inspired countless works of art and have influenced architecture, photography, and design. The Sun, in this sense, is not just a physical presence but also an aesthetic force that affects how we experience our surroundings. In addition to its nurturing aspects, the Sun can also pose challenges. Prolonged exposure to its ultraviolet radiation can harm living tissues, leading to conditions such as sunburn and increasing the risk of skin diseases. This dual nature highlights the balance required for life to thrive. Earth's atmosphere and magnetic field provide essential protection, filtering harmful radiation and shielding the surface from many of the sun's more dangerous effects. Without these protective layers, life on Earth would be vastly different, if it could exist at all. Humanity's relationship with the sun has evolved alongside technological progress. In modern times, there is growing interest in harnessing solar energy as a sustainable and renewable resource. Solar panels convert sunlight directly into electricity, offering a way to reduce dependence on fossil fuels and lower environmental impact. This shift reflects a broader recognition of the sun not only as a natural phenomenon but also as a key to future energy solutions. As technology improves, the efficiency and accessibility of solar power continue to increase, making it an increasingly important part of global energy systems. Culturally, the sun has maintained its symbolic importance across generations. It has been associated with concepts such as life, truth, power, and rebirth. Many traditions celebrate the sun through rituals, festivals, and stories that reflect its central role in human existence. Even in contemporary society, where scientific explanations dominate, the emotional and symbolic resonance of the sun remains strong. It continues to inspire curiosity, creativity, and a sense of connection to something larger than ourselves. Scientific exploration of the sun is still ongoing, with new missions designed to uncover its remaining mysteries. Researchers are particularly interested in understanding the mechanisms behind its magnetic activity, the heating of its outer atmosphere, and the precise behavior of solar particles as they travel through space. These questions are not only important for theoretical knowledge but also for practical applications, such as improving space travel and protecting astronauts from radiation. As humanity looks beyond Earth, the sun becomes a reference point for understanding other stars and planetary systems. By studying its properties in detail, scientists can compare it to distant stars, identifying similarities and differences that help explain how solar systems form and evolve. The sun serves as a benchmark, a familiar example that allows researchers to interpret observations from across the galaxy. In the grand scale of the universe, the sun is just one of countless stars, yet it holds a unique significance for us. It is both ordinary and extraordinary, a typical star in many ways but also the foundation of everything we know. Its presence defines our environment, shapes our experiences, and sustains our existence. Through continued observation, reflection, and innovation, humanity's understanding of the sun will keep expanding, revealing deeper insights into its nature and its place in the cosmos. As scientific understanding deepens, the sun increasingly becomes a bridge between present knowledge and future exploration. Its proximity allows scientists to test theories that would be impossible to examine directly in distant stars. By observing subtle variations in its light, surface patterns, and magnetic behavior, researchers refine models that explain how stars are born, evolve, and eventually die. In this way, the sun acts as a cornerstone of astrophysics, grounding abstract ideas in observable reality and offering a reference point for interpreting the vast diversity of stars scattered across the universe. One of the most compelling areas of study involves the sun's influence on space beyond Earth, particularly in regions that humans are only beginning to explore. As spacecraft travel farther from our planet, they encounter the outer boundaries of the sun's influence, where the solar wind slows and interacts with interstellar space. Understanding this boundary is crucial for future missions that may venture deeper into the galaxy. The sun, therefore, is not just a local presence but also a force that defines the limits of our immediate cosmic neighborhood. The relationship between the sun and human technology continues to grow more intricate. Satellites orbiting Earth rely on stable conditions to function effectively, yet they exist within an environment shaped by solar activity. Engineers and scientists must constantly adapt to the challenges posed by solar radiation and charged particles, designing systems that can withstand sudden changes in space weather. This ongoing interaction between natural forces and human innovation highlights the dynamic balance between dependence and resilience. At the same time, the sun inspires new forms of technological ambition. Concepts such as solar sails, which use the pressure of sunlight for propulsion, demonstrate how its energy can be harnessed in ways beyond traditional power generation. These ideas reflect a shift in perspective, where the sun is seen not only as a source of energy but also as a partner in exploration. By learning to work with its natural forces, humanity opens new pathways for traveling through space and expanding its reach beyond Earth. The future of solar research also holds promise for addressing some of the most pressing challenges on our planet. Climate studies, for example, depend on a precise understanding of how solar energy interacts with Earth's atmosphere and oceans. While human activity plays a major role in shaping climate, the sun remains a fundamental driver of environmental systems. Distinguishing between natural solar variations and human-induced changes is essential for developing accurate models and effective solutions. In education and public awareness, the sun serves as an accessible entry point into the broader field of science. Its visibility and importance make it a natural subject for learning, sparking curiosity in people of all ages. Observing a sunrise or sunset can lead to questions about light, energy, and the structure of the universe. This sense of wonder often becomes the starting point for deeper exploration, encouraging future generations to pursue knowledge and discovery. Philosophically, the sun invites reflection on humanity's place in the cosmos. It is a constant reminder that life on Earth depends on forces far beyond human control. Despite technological advancements, the fundamental reliance on the sun underscores a shared vulnerability and interconnectedness. This perspective can foster a sense of humility, as well as a recognition of the delicate balance that sustains life. Looking far into the future, the sun's eventual transformation will mark a turning point for the solar system. As it ages and expands, conditions on Earth will change dramatically, eventually becoming inhospitable for life as we know it. While this event lies billions of years ahead, it raises important questions about the long-term survival of life and the potential need to look beyond our home planet. In this sense, the sun not only sustains life but also sets a timeline that challenges humanity to think on a cosmic scale. Even with all that has been discovered, the sun continues to hold unanswered questions. Its behavior is complex, and many of its processes are not yet fully understood. Each new observation reveals additional layers of detail, often leading to further mysteries rather than simple conclusions. This ongoing process of discovery reflects the nature of science itself, where knowledge is continually refined and expanded. As humanity advances further into the modern age, the relationship with the sun is entering a new phase defined by both dependence and deliberate adaptation. What was once observed from afar is now studied with precision instruments, satellites, and space missions designed to approach closer than ever before. These efforts are not simply about curiosity, they reflect a growing need to understand how the sun's behavior directly affects an increasingly technological civilization. Power grids, communication systems, navigation networks, and even financial infrastructure rely on stable conditions that can be disrupted by intense solar activity. This reality has transformed the sun from a distant object of study into an active factor in global planning and risk management. The development of solar observation technologies has allowed scientists to monitor the sun in real time, capturing detailed images and data across multiple wavelengths of light. This multidimensional view reveals aspects of the sun that are invisible to the human eye, such as high-energy radiation and magnetic field interactions. By combining these observations with advanced computer models, researchers can simulate solar processes and improve predictions of solar events. Although forecasting space weather is still an evolving science, progress in this field is steadily increasing our ability to anticipate disruptions and prepare for their effects. At the same time, the sun is playing a central role in the global shift toward sustainable energy. As concerns about environmental impact and resource depletion grow, solar power offers a compelling alternative to traditional energy sources. Harnessing sunlight through photovoltaic systems and other technologies provides a renewable and abundant supply of energy that can be accessed in many parts of the world. This transition is not without challenges, including issues of storage, efficiency, and infrastructure, but ongoing innovation continues to address these limitations. The sun, in this context, becomes not just a natural necessity but a cornerstone of future development. The expansion of solar energy also carries social and economic implications. In regions with limited access to traditional power grids, solar technology can provide electricity to communities that were previously underserved. This has the potential to improve education, healthcare, and economic opportunities, demonstrating how the sun's energy can contribute to human progress in tangible ways. The decentralization of energy production, enabled by solar systems, may also reshape how societies think about power distribution and independence. Beyond Earth, the sun remains a critical factor in the future of space exploration. Any long-term human presence beyond our planet will require careful management of solar radiation and energy resources. Spacecraft, habitats, and protective systems must all account for the sun's influence, balancing its benefits with its risks. As missions extend to the Moon, Mars, and potentially beyond, understanding how to live and operate under varying levels of solar exposure will be essential. In this sense, the sun is both a resource to be utilized and a force to be respected. The continuing study of the sun also contributes to a deeper understanding of universal principles. By examining its life cycle, scientists gain insight into the processes that govern stars throughout the cosmos. This knowledge helps answer fundamental questions about the origins of elements, the formation of planetary systems, and the conditions necessary for life. The sun serves as a nearby example of these processes, allowing researchers to test ideas that can be applied on a much larger scale. At a more reflective level, the sun encourages a broader perspective on time and existence. Human lives unfold over decades, while civilizations span centuries, yet the sun operates on timescales of billions of years. This contrast highlights the vastness of cosmic processes and places human experience within a much larger framework. The steady light of the sun, shining across generations, connects the past to the present and extends into a future that will outlast current forms of life and society. In the end, the sun stands as one of the most significant and enduring forces in our existence. It is the source of light, energy, and life, shaping the environment in which all living things develop and thrive. From its complex internal processes to its far-reaching influence across the solar system, the sun embodies both stability and change, offering a constant presence that is never truly static. Its impact can be seen in the natural world, in human culture, and in the technologies that define modern life. Through centuries of observation and discovery, humanity has come to understand the sun not as a simple object in the sky but as a dynamic and intricate star with profound importance. Yet, even with this knowledge, it continues to inspire questions and exploration, reminding us that there is always more to learn. The sun connects us to the broader universe, serving as both a foundation for life on Earth and a gateway to understanding the cosmos. As we look to the future, the sun will remain central to both survival and progress. Whether through scientific research, technological innovation, or philosophical reflection, its presence will continue to guide and challenge humanity. It is a reminder of our dependence on natural forces, as well as our capacity to study, adapt, and grow. In its light, we find not only the energy that sustains life but also the inspiration to keep seeking knowledge and meaning in the vast expanse of the universe. Thank you for watching this video.